please read the section from your textbook on page 288. It's called Connecting Differential and Integral Calculus. So it turns out that the two teams were working on how to find slope of a tangent and how to find area under a curve because it could tell us distance traveled. And they didn't even think that the two problems were related. And then they found out that they were. Pretty cool. So that's this secret connection that we've been joking about. But that's what brings the two halves of calculus together and makes us study them at the same time. And we're going to have a more formal definition of this in section 5.4. It's kind of like the big reveal in chapter 5. But it's introduced in your textbook here in 5.3. So here's what we do. If you want to evaluate a definite integral, we can use an antiderivative. Maybe there's some function we don't know a geometry way to find the area under the curve. Here's an algebra way, a calculus way to find area under curve, to evaluate a definite integral. And it requires that we do that process that we were talking about back in chapter 4, is finding an antiderivative. Can you think of a function whose derivative would give you the function that you have? So here we go. If capital F of x is any antiderivative of little f of x, then in the integral from a to b of little f is equal to capital F of b minus capital F of a. So here's a great question. I want to evaluate the integral from 0 to pi of sine x dx. We're going to learn some slightly fancier notation to use, but we can do this because of what we just learned here. Can you think of any antiderivative of sine of x? If you can, write it down and call it capital F of x. So when I think of sine, I always think of cosine. They're like brothers. So if I take the derivative of cosine, do I get sine? No, if I take the derivative of cosine, I get negative sine. So the antiderivative of sine is negative cosine. I'm going to write myself a note. I'm going to think of an antiderivative of sine as negative cosine x. Now I could have said negative cosine x plus 3, or negative cosine x plus 17, or negative cosine x plus any constant. I could have written my plus c, but notice this is a very powerful statement up here. All I have to do is think of any antiderivative. So I'm going to go with capital F of x equals negative cosine of x. This integral from 0 to pi of sine x dx is going to equal capital F of b minus capital F of a. A is 0, b is pi. That's going to be negative cosine of b, which is pi, minus negative cosine of 0. So all I have to do is evaluate this. On the free response section, feel free to leave this unsimplified. But cosine of pi is negative 1, so negative cosine of pi is negative negative 1, which is 1. I have a minus, a negative, I'm going to add. Cosine of 0 is 1, and the integral from 0 to pi of sine x dx equals 2. Look at this next one. Can I find an antiderivative for secant squared of x? If I can, then I'm going to be able to evaluate this definite integral. When I see secant squared, I think, oh yeah, that's the derivative of tangent. I'm going to write myself a note, whoops, the capital F in this case is tangent x. All I need is any antiderivatives. That's why I haven't worried about a plus c on the end. Tangent x is an antiderivative of secant squared of x, because if I take the derivative of tangent x, I get secant squared of x. So here I go. I'm going to have f of b, so it's tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1, minus tangent of 0 is 0. So the integral from 0 to pi over 4 of secant squared of x dx equals 1. Take a look at this next one. I'm going to have to think a little harder about this antiderivative, but everything else is going to be the same. If I could think of an antiderivative of 4x cubed minus 6x, I'm going to be able to evaluate this definite integral. So here if I were taking the derivative of a polynomial function, I bring the old exponent down to the front to multiply, and I decrease the exponent by 1. Here, I'm going to try to build my capital F. I'm going to undo those operations in reverse order. So I'm going to increase my exponent by 1. So I had a 4. Here's my x. Instead of x cubed, it's going to be x to the 4th, and I'm going to divide by the new exponent. Minus, I have a 6. Instead of x to the 1st, I'm going to have x to the 1 more exponent, so x squared, divide by the new exponent. So it's not that important that you simplify, but you might find that the math in the next step is a little easier if I simplify. So I'm going to say that's x to the 4th minus 3x squared. So can I evaluate this definite integral? Yes. I'm going to find f of 2 and subtract f of 1. Like I said, we're going to learn some better notation to use, but you can answer this question now. So I'm going to write myself a note that f of 2 is 2 to the 4th minus 3 times 2 squared, which is 2 to the 4th is 16, minus 3 times 2 squared is 12, which is 4. I'm going to write myself a note that f of 1 is going to be 1 to the 4th minus 3 times 1, which is 1 minus 3 is negative 2. So this antiderivative, so this definite integral is equal to f of 2, which is 4, minus f of 1, which is negative 2, which gives a final answer 6.